Sanne van Waveren, which is a PhD student at KTH, is going to talk about leveraging non-experts informal methods to automatically correct robot failures. And I'll leave the stage to her.
Thank you. Okay. All right, thank you. Yes, so today I'll be talking about leveraging people who are not necessarily roboticists or programmers and formal methods to automatically correct system failures. And I'll talk about robot systems in particular, but the approach that I'll talk about today is applicable to any kind of decision-making system. So I assume most of us are familiar with reinforcement learning, but I'll just give a brief recap to freshen our minds. So reinforcement learning can be seen as a game-like setting in which an agent tries to maximize a long-term reward signal by trial and error exploration with the environment. And reinforcement learning has been shown to be successful to find optimal policies in complex decision-making and control tasks. For example, in robotics, a robot can learn how to run, so locomotion tasks, or autonomous driving. So these are tasks where it's difficult to explicitly model the underlying problem. Or, for example, robotic manipulation. The dream would be to just have a robot and set it up without having to explicitly program how it has to do its task. And reinforcement learning can actually learn the task without us having to do so. Let's see, yes. Reinforcement learning has been shown promising in learning the optimal policy for high-level actions, such as pick, place, chop, deliver, for example, in this cooking robot on the right. However, if we think of systems that have large state spaces, such as autonomous driving or robotic manipulation, as you just saw earlier, it becomes very impractical and costly to explore the whole state space. And the success of reinforcement learning depends on this exploration and this interaction with the environment to see what effects the actions have. And this becomes even more of a problem when we don't have a simulator. So the agent or the robot needs to rely on interactions with the physical world. And when we deploy reinforcement learning robots or systems into the world, the final policy might still fail. In this case on the right, the lettuce slice that it needed to make a salad now turned into a whole lettuce, and it first needs to chop it on the cutting board, but it doesn't know that. It didn't learn that during training. So safety and robustness remains a challenge for real-world safety-critical systems to be deployed when they use reinforcement learning. And we need ways to correct the robot's behavior or the policies while we can ensure the safety. And using non-expert feedback has become increasingly interesting to correct robot behaviors through demonstrations or corrections of the learned behavior, or through positive and negative feedback, which can take the form of numeric rewards. However, these techniques typically require the human to constantly monitor the robot throughout the whole process, and they lack formal guarantees on the system's behavior. Formal methods is a collection of mathematical techniques that are used to specify and verify systems' behavior. And one of those techniques is shielded reinforcement learning, and with the aim of ensuring safety of policies given a certain specification. So in this case, we can apply reinforcement learning while we still avoid unsafe actions. We can think of a shield as a teacher who only provides feedback, in this case, safe actions, when necessary. And so we proposed a policy repair approach in which we train a robot as a reinforcement learning system in the training environment, which is then deployed into a different environment, and upon failure, it queries a non-expert for feedback to correct the failure. And this feedback is used to generate a shield to correct the failure, and with this shield, we retrain the system so that it can avoid the failure on future occasions. And this way, robots or reinforcement learning systems do not need to fully rely on experts to recover from failures, and the resulting corrected behavior can be formally verified. We show in our results that shielded RL always learns the task successfully, which means that it learns how to avoid the failure on future occasions while being more data efficient and stable compared to using no shield. But of course, research never ends, so there are still some open challenges. For example, we have not automated the shield synthesis yet, and we have not deployed this on a real robot. So there are questions remain, for example, how we can automatically test how effective corrections are. Is the input from humans sensible, and are they actually correcting the failure at hand? And what level of abstraction is needed for the actions that the robot can perform and the states that the robot can encounter, so that they are intuitive for non-experts to understand? Because you can imagine maybe low-level control is not as understandable as higher-level actions like chop and place and pick. And how can we leverage the robot sensors for richer environment representations? How can we use the sensor information and fuse them together so that we can give rich information to non-experts, so that the situation and the environment of the robot becomes understandable for them, even if they're not on site? And answers to these questions will lead to help us develop robots that combine non-expert feedback and formal methods for automatic verifiable policy correction. So this was a very short talk. So if you have any questions, we have the Q&A here, or otherwise feel free to reach out to me via the contact details listed right here. Thank you.
Thank you so much, Sanne. That was a very interesting topic. I didn't know much about robotics myself, so definitely interesting to see. Okay, we have one question from Galina. Robots, autonomous things, sometimes in multiple ML algorithms, sensor fusion mechanism, and so on. If it receives feedback, how to determine which system it belongs to, if that makes sense?
Yes, so that's a great question. The work that I described in this short talk, we actually assume that the robot knows that it fails. It just doesn't know why it failed, and we are looking for corrections of the failure to identify the cause and then say, how can we correct it? For example, with the lettuce, we can say, like, if there's no more lettuce slices, first chop a whole lettuce and then pick a slice. But it's a very good question that if you have different parts and different modules in your robotic system, you need to know where the failure happened. And that's also related to the question of what information do we give to people? Because if you see a robot in its environment not doing what it should be doing, and it's not, a clear failure, it might be very difficult for people to understand what's going on. That's why we focus on, which I didn't mention super clearly in this talk, but we focus on changes in the environment that cause the robot to fail. So in this case, the lettuce slice is no longer available. Or you can imagine that in your training environment, you have learned to navigate on a linoleum floor, and then suddenly you get stuck on a carpet because someone in his home has a carpet, and you need to learn to avoid carpets in that case. So it's changes in the environment that are obvious to the outside world in that case.
Thank you. Makes sense. And then we have another question, which is, what is the funniest example of robot failing that you have seen?
Oh, that's a great question. I definitely have seen some that I'm like, ooh, I hope people are not gonna not work with robots at all anymore because of what happened here. I did an escape room with the robot as a first study during my PhD, and one of the robot actually basically I lost the network connection, and I was actually controlling the robot, so it was going backwards. And it didn't stop going backwards, and so it drove into like this line that I had put up, and it heeled over, almost falling backwards, and the person was holding it like, please don't fall, please don't fall. I'm not sure if it's funny. It was a bit scary at that moment, but now I can laugh about it a little bit.
That's
a great question.
That's a very funny example. I can imagine the small robot falling and being super cute.
Yes, because it looked like a very cute, it's a humanoid robot, so it looked like a little kid a little bit. So, it falling over, the participant was really like, oh, please don't. Yeah.
Thank you so much for sharing this talk and this example. It was super interesting.
Thanks for having me.
To learn more. Thank you.